All right, so here's the last of class 14, where I wanted to put together the fundamentals of the vector loop method for finding velocity analysis. This is the inverted crank slider. It's the fourth of the different variations that get used. And the way that we set the thing up is very similar to the crank slider or the slider crank, in that the direction of the vectors are the same. Really the big difference here is there's stuff that doesn't go away. And this value of b, it does change because this thing does slide back and forth. There is an angle that's going to be placed in between theta 3 and theta 4. It could possibly, it's usually fixed right in there, so we're going to have to adjust for that. So if we were to write this thing out, once again, I'm having a hard time with my pen once again. We have A, E, J theta 2 minus B, E, J theta 3 minus C, E, J theta 4 minus D equals 0. And you can see, okay, so all those minuses are all because the directions of the vectors, as we've chose them, are backwards from the loops. So if we substitute in Euler's identity right here, I'll write it down so I can try to get it all on one line. A omega 2, whoop, sorry, I'm going to take the derivative of it first. So A omega 2 J E to the J theta 2 minus B omega 3 J, don't forget your J's, J E J theta 3 minus C omega 4 J E J theta 4, and then minus, oh no, the D goes away. But we got a problem. I'm sorry. Let me go back. Let me go backwards. My bad. Here is the real big difference here. Is when we get to this term, we need to adjust. We have to take the product rule of it. So A omega 2 J E to the J theta 2, right, minus B omega 3 J E to the J theta 3. But now we have to go minus B dot, right? And is there a J? Oh yeah, we do need to take a J as part of this. A J does fall down from there. And then E to the J theta 3. It's just that we take as if J theta 3 does not change, so therefore there's no theta dot and no omega when we do the B dot of the thing. And then minus C omega 4 J E to the J theta 4 equal to 0. So that's a little different than you might expect. It's always that J dropping down always bothers me right here, right? That we're going to have a J. I should make it look like the same J as before, right? There's a J, and the dot looks weird, right? So that one always bothers me, and I had to really get convinced that the J was going to fall out of the E and come down. But it does. It's an important distinction to make. If we go ahead and plug in the Euler identity in here, do I want to write this whole thing out? I guess I'm not sure anyone's going to really object to me not writing it out. If I just take the thing apart and plug Euler in, and I separate it out into the imaginary. So that goes A omega 2 times the cosine of theta, right? And a theta 2 minus B omega 3 cosine of theta 3 minus b dot times the cosine of theta 3. I have to fix that theta, right? Minus c omega 4 cosine of theta 4 is equal to 0. And then just to vary things up, here's the real. We get negative a omega 2 sine of theta 2 plus b omega 3 sine of theta 3 plus b dot sine of theta 3 plus c omega 4 sine of theta 4 equal to 0. And either one of these we could solve for b dot. But let's go ahead and solve the real one. All right. So we get b dot is equal to negative a omega 2 sine theta 2 plus omega 4 b sine of theta 3 plus c sine of theta 4 all divided by cosine of theta 3. And that's this right here is equation, not EG, it's equation 630a right there, okay? And then, so, like, this is one that we would use, but we need to know omega 4 right here. Like, most of the time it would be omega 2 in this type of a configuration, but we still need to know omega 4 to be able to solve this. So we come back in here and we say that we substitute this back into the imaginary, right? Or we could have done it the other way around. But what we're left with is that omega, and then there's also some trig identities that we have to apply to this. It was a, wow, that thing really is going crazy. A omega 2 cosine of theta 2 minus theta 3 divided by b plus c cosine of theta 4 minus theta 3. Right, and so now if we have omega 2 as an input, we're able to get omega 4. Once we have omega 4, we're able to put it back in there and find, this is called the velocity of slip right here, by the way. Velocity of slip. And it's the changing of the length of this right here, but we treat it as if that's the direction that it's going. That velocity is treated right there. So this is another variation, and another one that we want to try to do. Some angle, by the way, the angle that we want to look at right here, remember that that's going to be equal to theta 3 minus theta 4. So we could actually substitute that into down here in the bottom of this equation right in there. So that's the end of the lecture part of the inverted crank slider.